Hello, welcome to part 2 of the Thermochemistry Vodcast. We're going to start with Roman numeral 4, chemical energy in the universe, going from small calorimetry experiments to looking at the changes in chemical reactions and how that drives everything that happens in the universe. Pretty exciting stuff. So, Roman numeral 4, chemical energy in the universe. Here's some terms. Thermochemistry is the study of heat changes that accompany chemical reactions and phase changes. For most of this year, we have focused on just the actual substances, but the energy is a really vital and important part of all the chemistry that happens. It does a lot of work for us. We have to learn to control it and use it to the best of our abilities. Enthalpy is a fancy word for heat. It's the heat content. But don't confuse that with temperature. Heat includes not only that kinetic energy from the motion, but also the potential energy of the formation of new bonds, the motion within the molecules. There's a lot more to heat content than just the temperature of a substance, the phase something's in, etc. The symbol you'll see is delta H of a reaction. That is a symbol for enthalpy, and it is the difference between how much energy the products has and how much energy the reactants had to start with. That's what we can measure in a calorimeter, or we can actually look up in something called the Merck Index or online, lots of different places. These numbers have been cataloged for our convenience. So here's a diagram to help you see how this all happens. I'm going to put in an axis. On the y-axis here is, let's try that again. Okay, here's a diagram to help you see this a little more clearly. I'm going to add some axes over here. Energy on the y versus reaction progress. Roughly time, but not necessarily proportional to the time. So if we have our reactants, a certain amount of energy they contain internally, that potential and kinetic energy that they have, when they come together and they react, there's some amount of activation energy needed, this increase in energy to collide and react in a certain form. The chemicals have to come together and often produce a transition state, some combination of the reactants that right before they break into new products, there's this sort of larger transition molecule. So the reactants come together with a certain amount of activation energy, and then they can break down into the products, which always have less energy than the transition state, but sometimes they have even less than the reactants. In this particular picture, you can see that if we do products minus reactants, we're going to end up with a negative delta H of reaction. The products ended up more stable with less energy than the reactants started with. If, however, we had the reactants ending up with the products ending up with more energy, our delta H would go from here to here, products would be higher, and so we would have a positive delta H. So for an exothermic reaction, we call that a negative delta H. And for endothermic, we call it a positive delta H. All right, so when we put it into a reaction, we can now quantify these changes that are occurring in the substances. So when sugar, C6H12O6, burns or metabolizes in our body, no matter which way it goes, it produces negative 2,808 kilojoules for every mole of sugar. So if you consumed 3 moles of sugar, which would be a lot, you could know that you had 3 times this amount of kilojoules produced in your body, released all that energy for you to go and use. Specifically for a combustion like this, that's called the enthalpy of combustion. And these are again measured and tabulated for our use. You can go look up. It's sort of like the calorie count of food would be its enthalpy of combustion, but you can also find it for different kinds of fuels, jet fuel versus diesel fuel versus gasoline, and compare energy sources that way. So it's a very important and useful number. You may notice that in a lot of these terms, there's this little degree symbol. It doesn't mean degrees in this situation. It means that what you have found is a standard enthalpy. That means that it was measured at a standard set of conditions. For thermodynamic values, that's at 1 atmosphere pressure. That's just like it was in gas laws, but in this case it's 298 K rather than 273 K. Go figure. All right. So let's practice one of those problems. If we find that the heat of combustion for methanol is 726 kilojoules per mole, of course that's negative because it's a combustion, how much heat is released if we have 82.1 grams of methanol? All right, so as in any stoichiometry equation, we need to change grams to moles. So methanol has a molar mass of 32.05 grams in 1 mole. And for every 1 mole of methanol, you have 726 kilojoules of energy released. That produces, go ahead and calculate, get a number, 1,860 kilojoules of heat released for those 82 grams. It's probably about 100 milliliters of methanol. And you could compare that to the heat released in some other types of fuels. All right, another approach to calculating the heat of a reaction is Hess's law. This is useful when you are trying to determine the heat of a reaction that is not easily measured directly. For instance, the lab that we're going to do next week is the combustion of magnesium. We have combusted magnesium, but as you can imagine, that would be difficult to contain and to collect, say, in a styrofoam cup of water, because you need to absorb the heat into something that you can measure a temperature change in. So we're not going to be burning the magnesium directly. We're going to do a series of reactions that give us the same end result. Hess's law dictates that can work. If 2 or more thermochemical equations can be added to produce a final equation for a reaction, then the enthalpy change for the final reaction equals the sum of the enthalpy changes for the individual reactions. That is complicated, but think of it in simpler terms. Many of us drive to Stinson Beach for lovely weekends such as this one. And rather than going directly from San Anselmo over to Stinson, we go around. We can go up and through Olima, or you can go down from Mill Valley and back up, or if you really like windy roads, you can go this way. But as the crow flies, we end up driving a lot further than 10 miles to go that net distance. We can go north a certain number of miles and south a certain number of miles, and you subtract the north from the south, you end up with the net change, and you get the 10 miles. In chemical reactions, we have, instead of north and south, we have positive and negative. And so if you have several steps, some endo and some exothermic, and you add them together, your net change is your heat of reaction for the overall reaction. Let me show you an example. Okay, so if we were to look for a thermochemical equation between ethanol, C2H5OH, and oxidize it to form acetaldehyde, C2H4O, and water, we would end up with, I believe this is a 2 and a 2 and a 2, and I think that's balanced with this reaction. This, by the way, is one of the steps in metabolizing ethanol in our bodies. Just to put this in context. But this is a reaction that it's hard to know the thermochemistry of, because it doesn't stop right there. A lot of other chemical reactions take place when you have these all together. So you can look up the heats of combustion of the acetaldehyde and the ethanol. So here's acetaldehyde, here's ethanol, and they both produce carbon dioxide and water. But what's cool is when you combine them in the correct order, you can get this overall reaction. Let's just look at it a second to see if we can imagine that, and then I'll show you on the next slide. The acetaldehyde here is written as a reactant because in the combustion it's the reactant, but we need it as a product. That is a 2, by the way. We need it as a product. So it doesn't mean that this reaction here is not useful. A is very useful, but what we'd have to do is reverse it so that when we add the heats together, it will be in the product location. Now, when we reverse it, we just simply have to change the sign. Instead of north, we're going south. Instead of going exothermic, we'll be going endothermic. The ethanol, however, is going in the right direction, but I need 2 of them. So for this one, I'm going to have to multiply it by 2, and therefore I'd get double the heat. I'd have to multiply the value by heat. So here's what it looks like when you add them together. So here's the acetaldehyde reversed. Notice the heat is positive now. The ethanol has been doubled, and we have double the energy. And you can see how the carbon dioxide showing up as a reactant and a product in the equal quantities, they can be canceled, just like the spectator ions that we talked about earlier this year. Here are some water molecules on both sides. Now I have 4 here and 6 here, so 4 of them cancel out, and I'm left with 2. 5 of the oxygens can cancel out, leaving us with 1. So now we bring down what's left over. 2 ethanols, an oxygen yields 2 acetaldehydes plus 2 water molecules to give you, add these guys together, negative 349 kilojoules. Pretty cool. We'll be practicing this in lab with our heat of combustion of magnesium. All right. We can also use the idea of Hess's law to figure out the energy of any chemical reaction just by knowing that if we know how much energy it takes to produce every product in the reaction and every reactant, as we talked about earlier, we can just take the products minus the reactants to get the overall heat of reaction. Let's try it. Okay. So here are those standard heats of formation for those chemicals in the ethanol oxidation reaction. All right, so what we want is the delta H of reaction, which equals the sum of the products first. So sum of I need two acetaldehydes. So I need 2 times negative 166 kilojoules, because it's kilojoules per mole, and here's 2 moles, plus 2 times the kilojoules per mole of water. Block those off. That's the change in heat of formation for the reactants, how much energy it takes to make those chemicals from their elements, minus the delta H of the reactants. We've got a number here for ethanol. It's 2 moles of it times negative 277.7 kilojoules. And when you add those all together, do the math, you should get, negative 348, just like we did when we did the version where we had the 2 combustion reactions added together. Different numbers, but energy is conserved, and so it always should turn out to be the same value no matter how you get to the end point. Just like you always get to Stinson, no matter how you go or how far you end up driving overall, the net change is always the same. Same thing here. All right, now let's take a step back. Not only is our chemical reactions trying to release heat generally, they also are trying to get more disordered. So entropy is another concept of what drives all the chemistry that's happening in the universe. It's a measure of disorder or randomness, and spontaneous processes always result in an increase in energy. Spontaneous meaning some reaction that would happen on its own. Not always quickly, but they will occur over time. For instance, rusting is a spontaneous reaction, even though it's very slow. Lighting a match is also spontaneous, even though it's quick. It's not about the speed, it's about whether it will happen. Photosynthesis is non-spontaneous. It won't ever happen on its own. Energy has to be put in. The sunlight has to hit the plant for photosynthesis to occur. Okay, entropy change is just like enthalpy change in that it's a difference between the product enthalpy and the reactant's enthalpy. Okay, things that affect entropy are a change of state. For instance, if you are going from a solid to a liquid to a gas, the particles are going from more ordered to more disordered to very random and spread out. This is always an increase in entropy, S being the symbol for entropy. If you're dissolving a gas into water, that's taking that gas and making it more ordered. So in this case, that would be a decrease in entropy. If you change the number of gaseous particles, for instance, you do a reaction that goes from 1 mole of gas into 4 moles of gas, like maybe a combustion or an explosion, is increasing the number of gas particles, then you would be increasing the entropy. Dissolving a solid or liquid to form a solution, that would also be an increase in entropy. Things are spreading out. Finally, change in temperature. I bet you can guess that when temperature increases, the entropy also increases and vice versa. All right, so let's put them all together. The entropy and enthalpy are useful in chemistry, especially when you're trying to control and use a chemical reaction, to think about something called free energy. Free energy is chemistry that can do work for us. It's, say, releasing heat that can move a turbine and generate electricity, or move something, move a piston in an engine to cause the car to move. Chemistry is useful in that way, not only making new products, but also changing energy around to do work for us. And so we need engineers, especially chemical engineers, have to think a lot about harnessing energy in the most efficient way possible. So here's the equation that is very useful. To understand how much free energy a system has, you have to think both about the enthalpy and the entropy. T is temperature in this case. So things spontaneously want to lose energy. They want to become a negative delta H, and things want to be more disordered. Well, let's see how that plays out for free energy. So if your delta G is negative, that means it must be spontaneous, because if you have what most things tend to do, you have a negative delta H and a positive delta S, releasing energy, getting more disordered, you have a negative delta G, because delta G would equal a negative value minus temperature times a positive value. So a negative minus a positive is always going to give you a negative value. So delta G is negative. It is spontaneous. It's releasing free energy to do lovely work for us. Combustions are an example of this, where things are always spontaneous. They will always go on their own under the right conditions. Now, if something's positive, it will be non-spontaneous. We talked about photosynthesis being non-spontaneous. And if we think about it, the delta G of photosynthesis would be a positive delta H, because energy is absorbed, endothermic, minus temperature times a negative delta S. A positive minus a negative is always going to be a positive, so photosynthesis is non-spontaneous and the delta G is positive. Okay, so the overall equation is this. You will not, on the test, have to do the math for this equation, but you will have the opportunity to get some extra credit if you do calculate it. So here's an example. We will be doing a very awesome hot demo next week where we burn thermite. Thermite is a combination of aluminum powder and rust, iron oxide. And when you get them to react, given enough activation energy, it will produce molten iron and aluminum oxide. This used to be used to, say, weld railroad ties together, because it provided a lot of chemical energy out in the field to make the molten iron. And you didn't have to have any other torches, etc. Now, if you are feel like being challenged, I've given you all the heat of formations and the delta S values for all of the substances in this reaction. In the summary section, I'm going to put a place for you to write in your delta H, your delta S, and your delta G values, and get a little extra credit. Now, please be honorable and only input numbers if you yourself have done the calculations, and we'll talk about it and see this awesome reaction live.